Okay, good morning and welcome back to the class, children. We were discussing understanding quadrilaterals. We have almost gone through 4 classes so far. We are in the verification of the exterior angles and the interior angles. We have seen that the sum of the interior angles of a 4-sided polygon, that is the quadrilateral, is always equal to 360 degrees. This is the result we have seen in activity 1. And then in activity 2, we have taken up the exterior angles and see that for any n-sided polygon, the sum of the exterior angles will always be equal to 360 degrees. So, 2 important results we have verified in our activity, and today we are going to further move on with these results to solve a few problems in the exercise 3.2, which is there in your textbook, page number 44. So, please keep your textbooks with you. I may take up a few problems and try to apply the results that we have verified so far to solve the given problem. So we will take up the first one here. I hope you are looking at the textbook at page number 44. This is exercise 3.2. In the first figure, you have a triangle whose exterior angles are given to you like this. Okay, the exterior angles at the 3 vertices, here it is given as 125 degrees. Then you have the second one, again given as 125 degrees. And here you are asked the third exterior angle as x, which is marked there. You are asked to find the third exterior angle. So, which is the property that you would be using here? The exterior angles of any n-sided polygon. It can be a 3-sided polygon starting from the triangles to any n-sided polygon. N can be any natural number. So, we know that the sum of exterior angles of any n-sided polygon.
Voice is not audible, ma'am.
Voice is breaking. Is it so for all of you?
No, ma'am.
No, ma'am, it's audible, ma'am.
See, there is some connectivity issue, my dears, on your side. Please check and verify if you are at a place where the connectivity is secure and fast. Because it is not a common issue that I have to address to. Alright. So the sum of the exterior angles of any n-sided polygon is always equal to 360 degrees. Here you have a 3-sided polygon, that is a triangle. So here also you have x plus 125 degrees plus 125 degrees, which are the 3 exterior angles for the given triangle, which will be equal to 360 degrees. So you're getting your simple equation here where you have to solve that equation as x plus 250 degrees equals 360 degrees, or your third exterior angle will be 360 minus 250 degrees, which will be equal to, what is 360 minus 250? Your x should be equal to
110.
110 degrees. So this is how you find the third exterior angle using the property of the exterior angles of any n-sided polygon. So similarly, you should be able to do it for the next figure where it is a pentagon given to you. Alright. So that you should be able to try on your own. I am not taking up that problem. We will move on to the next problem 2. Take this down quickly. We will move on to the next problem. Now, before we move on to the next problem, I have a question. You don't know, this is bothering me. Suppose my exterior angle for this triangle is given as 125 degrees. Say I name the triangle as ABC. Is there any way that I can find the interior angle at A? If this exterior angle is given as 125 degrees, is there any way in which I can find the interior angle at that point A or the vertex A?
Yes, ma'am. We can find it by linear pair.
Yeah, using the linear pair axiom, you should be able to find out this angle, which will be equal to 180 minus 125 degrees. Alright, so this is an important result that you should be able to remember. Wherever it is required, we will apply. This is the relationship between the exterior and the interior angle at a given vertex. If I know the exterior angle, I know the interior angle will be a linear pair to the exterior angle. Similarly, if I know the interior angle, the exterior angle will become a linear pair to the interior angle. This you have to remember. This is the result very frequently we may be using in many more problems that we are supposed to take up. So we will move on to the second one now. Okay, the second problem says find the measure of each exterior angle of a regular polygon of n sides. The n is given as 9 sides here. I take the n as 9-sided polygon. It's a 9-sided polygon. I have to find the measure of each exterior angle for this 9-sided polygon. How will I find out? Using the same exterior angle property. I have been given that the polygon is 9-sided. Now, how will I use this information to find out what is the exterior angle of...
audible.
Ma'am, 360 divided by 9.
Yeah, 360 divided by 9. Why should I divide it with 9?
Ma'am, because it has n sides, which the n is equal
If
to
a
9.
polygon has got n sides, it means it has got n vertex, and hence every vertex will have an exterior angle. So there are n exterior angles which will account to as 360 degrees. All the exterior angles of any n-sided polygon will always sum up to 360 degrees. This is an important result that we have verified in our previous class. That's why I'm insisting, please verify it yourself. I have shown you how the activity is done. Many of you have done it, but a few more of you have not shown it to me for, I don't know, the reasons best known to you. If you have not already completed it, please complete it so that that result is well understood and assimilated by you. You should know that whenever I add the exterior angles of any n-sided polygon, it will always sum up to 360 degrees. Because there are n sides, that means 9 sides in this given polygon, it has got 9 exterior angles. And because it is a regular polygon, that is the word here. It is a regular polygon. What do you mean by a regular polygon? We have discussed regular and irregular polygons.
All its
When do you
sides
say a polygon is
will be
regular?
equal.
Ma'am, all sides are equal, ma'am.
Yeah, when all its sides and all its angles are equal, then such a polygon is called a regular polygon. Now in our question, it is said it is a regular n-sided or 9-sided polygon. So I know all the angles are equal. That means that 360 has to be divided with 9 to get the measure of each exterior angle. This division is possible only when the polygon given is regular, because all the angles are equal. I simply have to divide 360 with 9 to get the measure of each exterior angle. But if it is not a regular polygon, then this division will not allow me to find the exterior angle. Why do you think so? Why can't I divide it with 9 when I have the condition that it is an irregular polygon? Why can't I divide it with 9 there?
Ma'am,
The measurement of other angles may differ.
Yes, they may be different. The angles may be different. Only condition is the sum will be 360 degrees. But they can be of different measures if it is an irregular polygon. But because in my problem very safely it is said it is a regular polygon, I am dividing 360 equally into 9 parts, and each of that part will be the measure of each exterior angle. So I know by the angle sum property again, that is sum of exterior angles.
Ma'am, please write this side, ma'am. We can't see that side.
You can't see? I thought I am adjusting. Is it all right now?
If we
Is
keep
it
the
all right
mobile
now?
horizontally, we can see, ma'am.
Sorry, I didn't hear you.
Ma'am, if we keep the mobile horizontally, we can see, ma'am.
Okay, I think I am adjusting seeing my view. That's why even I am not worried, but somebody is telling they are not able to see. I am changing the flap according to the angle which is required. I hope I am within the cover area. Okay, if there is any more problem, please tell me. Sum of the exterior angles is equal to 360 degrees. Number of sides equals 9. Since it is a regular polygon, measure of each exterior angle will be equal to 360 degrees divided by 9, which will be equal to 40 degrees each. So each exterior angle for a regular 9-sided polygon will be equal to 40 degrees. Okay, this is one variety of problem. Maybe you can do it for a 15-sided polygon on your own. When the given polygon is a 15-sided regular polygon, I know the measure of each exterior angle will be equal to 360 divided by 15, which you can calculate and find out. Alright, now moving on to the next problem. Maybe I'll use this part of the board, should be visible. I'm in the third one. This is another variety of problem based on exterior angle property. Can I move on to the next one? Is it done? Anyway, I'm recording the meet, children, so you will get your link. Don't worry. If you are a little slow, never mind. You can view it later on after the class is over and complete your notes. Okay. Now look at the third one. How many sides does a regular polygon have if the measure of each exterior angle is 24 degrees? So each exterior angle is given to me. In the previous problem, I had the number of sides given to me. Here I have each exterior angle is equal to 24 degrees. Now the question is, how many sides will this polygon have? So when the sides were given and it was told it is a regular polygon, I divided 360 with the number of sides to get the measure of each exterior angle. Okay, this is one variety of problem. Now in the next problem, they have not given me the sides of the polygon. They have given me that each exterior angle is 24 degrees and moreover it is a regular polygon. So the regular will tell me that all the angles are equal. So all the exterior angles in this regular polygon is equal to 24 degrees each. Now the question is, how many sides does this polygon have? How do you think you can find this?
Ma'am,
When I
360.
add all the exterior angles of this polygon, definitely I am getting 360 degrees because that is my property for a exterior angle of a polygon. Any n-sided polygon, when I add its exterior angles, it will sum up to 360 degrees. So now I am saying that one of my exterior angle is equal to 24 degrees and it is a regular polygon. Means what did I understand? All the exterior angles of this polygon is equal to 24 degrees each. So how will I find out the number of sides of this given regular polygon?
Ma'am, 360 divided by 24.
Why are you dividing 360 with 24? Because you have to find out how many 24s will add up to 360 degrees. That's why you're dividing that. So if there is one exterior angle which is 24, the second one also will be 24. So how many times when you add 24 will you reach 360? That will tell me how many such angles are added and that will be the number of angles in that number of sides in that given polygon. So how will I write this? So exterior angle property, according to the exterior angle property. Can you see till the end what I am writing?
Yes, ma'am.
Yes, ma'am.
According to the exterior angle property, what do I know? But for a regular polygon, when I add up all the angles, it will be equal to 360 degrees. So I can write 24 plus 24. So many 24s, I don't know how many 24s will add up to 360 degrees. So this is what we have to find out. How many 24s when I add up, it will become 360 degrees. Or how many times should I add 24 so that it becomes a 360 degree. Therefore, the number of sides will be equal to the 360 degrees, which is the total or the sum of all the exterior angles divided by the measure of one exterior angle, which is 24 degrees. Because it is a regular polygon it is given, I know that all the angles will be equal and hence I have to see how many 24s can be added to make 360, which is equal to. Could you solve that? 360 divided by 24.
Ma'am, 15.
Are you getting 15?
Yes, ma'am.
Good.
Yes.
So the number of sides will be 15. So once you know the exterior angle for a regular polygon, you can find its sides. Or if the sides are known, you can find the individual exterior angle for the given regular polygon. Both ways are possible only when it is a regular polygon, because all angles and all sides are equal in regular polygons. So we'll take up one more problem and then move on to the different varieties of quadrilaterals next. One more variety which I wanted to discuss with you. This is problem number 4. Okay, are you looking at the fourth problem? How many sides does a regular polygon have if each of its interior angles is 165 degrees? Again, it is a regular polygon, so all sides, all angles are equal. The only difference is instead of the exterior angle, the interior angle is given. Now, how am I going to use this information to get back to my exterior angle property and solve the problem? You have to think. I gave you a hint in the previous problem also. There is a relationship between the interior and the exterior angle at a given vertex. What was that? I just told you now. If I know the exterior angle at a particular vertex for a polygon, should I be able to find its interior angle?
Yes, ma'am, by linear pair property.
Yes,
Yeah,
ma'am.
by using the what? Which was the
Linear
property
pair
that we have
property.
used? Which was the
Ma'am,
property
linear
we
pair.
used? I couldn't hear you.
Ma'am, linear pair.
Yes, the linear pair axiom. So here I am given that the interior angle of a regular polygon is equal to 165 degrees. That means all its interior angles are going to be 165 degrees each. Now, if 165 degrees is the interior angle, can you go and find out what will be the exterior angle for this regular polygon? Each exterior angle will be equal to 180 minus 165. How much is that?
Ma'am, 15.
15 degrees. So each exterior angle is going to become 15 degrees. All right. Each exterior angle is going to become 15 degrees because again in the problem it is given that it is a regular polygon. So all the exterior angles are going to be equal to 15 degrees each. Now I know by the exterior angle property that the sum of the exterior angles will become equal to 360 degrees. So how many 15s when you add will you get 360 is what you have to find out. That is, in other words, you have to find out 360 divided by 15, which will give you the measure of, the number of sides of a given regular polygon. So how will you write the statements here? Interior angle of given regular polygon is equal to 165 degrees. Alright, so it is equal to 165 degrees. Therefore, each exterior angle will be equal to 180 minus 165. I hope you understand why it is 180 minus 165. Because at a given vertex, the interior and exterior angle together will form a linear pair. So if I know one of the angle, the other one can be the supplement of that angle itself. So this will become 15 degrees. Now, number of sides, the regular polygon using my exterior angle property will be 360 degrees divided by 15 degrees is each exterior angle. So divide the 360 with 15 and tell me what will you end up with?
Ma'am, 24.
24.
Yes, you will have a 24-sided polygon. Alright. So the sum of the exterior angle is equal to 360 because each exterior angle is equal to 15 degrees. Please pin my screen so that even if somebody is trying to speak or there is some disturbance, the screen doesn't get shifted. Please pin on my screen so that you're seeing only my screen. So because each exterior angle is equal to 15 degrees, 360 divided by 15 will give you 24. So that is the number of sides given. polygon, given regular polygon. So these were the varieties of problems which we require to discuss with respect to the exterior angle property. Now next we are going on to the different kinds of quadrilaterals. So there is a video which I shall be sharing with you right now where we are discussing the different varieties of quadrilaterals. I'm not going to play the complete video because we are having time only for another 10 to 15 minutes. So I will play the video where we are going to discuss only on the trapeziums and the kites. All right. Maybe in the next class, I will continue more about kites, where I will be using the GeoGebra applet to tell you how the properties of kites are discussed. Now, this is also a video which I have only made. This is my video only. I think I will share this link with you after the class so that you can again leisurely go through the entire video. Though I am not going to play it completely here for you now. All right, so let us go and listen to that video. I will not be interfering in between because it is just an introduction where I'm talking about the trapeziums and the kites and how they are different from each other and how they are special varieties of quadrilaterals. So give me a minute. Let me share my screen. Yes. 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 Is there anything that you want to share with me? Shall I? Okay. Yeah, can you see the screen that I have shared?
Yes, ma'am.
Okay, now
Yes,
I'll just maximize this. I will stop in between and ask you if it is audible because I have my doubts whether it will be audible. So I'll just play for a few seconds and get back to you. Okay.
Okay, ma'am.
So I just start with my chapter on quadrilaterals, my dear children. Hope you all of you are very fine and healthy, staying at home. So we had to. Is it audible?
Yes, ma'am. Yes, ma'am.
Okay. So I play it further. Please listen carefully and look at the visuals that are shown to you. 2 sessions of quadrilaterals already. So I'll just quickly sum up what was done in these 2 sessions.
Okay.
We had largely seen the types of polygons. There were 2 classifications. On one classification, we had got the convex and the concave polygons. Then we also had the classification as regular and irregular polygons.
Okay.
Then we moved on to the angle sum property of quadrilaterals, which we have verified also using various activities. And then from there, we switched over to the exterior angle property of any n-sided polygon. So this was what Sarita ji had done for you in the last part of this chapter. And later on, she also had solved problems based on the 2 above said properties. So I think now you would be clear with all this, which is done in 2 parts so far. So today we will be taking up exclusively only the quadrilaterals and its special varieties.
Okay.
So I think I'll go on to that learning point that we have for today.
Yes, ma'am. Please.
Yeah, we have the types of quadrilaterals to be classified into 2 major categories. That will be the trapeziums and the kites. Followed by that will be the parallelograms, which is again taken separately because it has got some special attributes which we shall be seeing today.
Okay.
And then from there we will branch out to again further special varieties of parallelograms. They will be in 3 categories as the rhombus, the rectangle and the square. So this is exactly what we are going to see in total in this 40 minutes today.
Okay. Shall we begin, ma'am?
Yes. Yeah. So I start with the trapeziums. I said I'm going to start with the trapeziums, which is a major variety of the quadrilaterals. So now in front of you in your screens, you have 2 sets of polygons separated and shown. So now you're going to observe them carefully and try to see if there is any difference between the polygons separated in set 1 and those shown in set 2. Now you can observe that for 30 seconds, then I'll get back to you. Yes, maybe you would also have seen as the same observations that I'm going to tell you. Now in set 1, you see all these polygons are four-sided polygons.
Right.
So we have already described the four-sided polygons as the quadrilaterals.
Right.
And there is something extra. Apart from being a four-sided polygon, there are some arrow marks put here. And we know when these arrow marks are put, we know they indicate that those two lines where the arrow marks are there, those will be parallel lines. So what do I see which is common in all these four quadrilaterals? I see that the opposite sides, one pair of opposite sides in each of these quadrilaterals are parallel.
Parallel.
Now let us shift on to the second set. Now in the second set, I have these two polygons can be categorized as quadrilaterals because they have four sides, but there is something more here in this polygon. Now this is not a four-sided polygon. It is a five-sided polygon, and we have already seen, or we have labeled a five-sided polygon as a pentagon. Now here we don't have these arrow marks in these two quadrilaterals that we have. That means they do not have any parallel sides at all. So from this classification, I am just focusing your attention on one major attribute of the quadrilateral that we are going to study.
Okay.
So here, those quadrilaterals which have one pair of opposite sides parallel will be called the trapeziums. This is what we are learning in the beginning today. Now, coming to the second set, none of these are having the attributes that we have described in the previous set.
Right.
If they are quadrilaterals, they did not have the parallel lines. And in case the parallel line was visible in this third polygon, it was not a quadrilateral. So this set of polygons, we cannot call them the trapeziums. So based on these attributes and this learning, now we can go and generally define a trapezium as a quadrilateral with one pair of opposite sides which are parallel. So this is the first branch we have come out of. So I hope you have understood what is a trapezium. So trapezium is a quadrilateral. It is a special variety of quadrilateral where only one pair of opposite sides will be parallel. All right. So this is a very, very important learning point for you today. So in the set of quadrilaterals, the first variety that we were able to classify was the trapezium, which is a quadrilateral with only one pair of opposite sides which are parallel. That is the quadrilaterals with this special attribute of having one pair of opposite sides parallel will be termed or classified as a trapezium. Now further, in a trapezium itself, you have a special variety. So I wanted to mention about this to you.
Okay.
So look at this trapezium here. You are seeing that one pair of opposite sides is already marked to be parallel. But there is something extra also over here. These are the two non-parallel sides that you have for the trapezium. Now they are marked as equal. That means the lengths of these non-parallel sides of the trapezium happen to become equal. So if I come across such a trapezium where the non-parallel sides are of equal length, then they are given this special name, which is the isosceles trapezium. You can draw this figure and label the two non-parallel sides to become equal and then give it this special name called the isosceles trapezium. So I hope this is understood, my dear children, because this is a variety which I wanted to discuss with you. Though it's not part in your textbook, I thought this is something that you have to know. What is an isosceles trapezium? Any doubt so far?
No, ma'am.
Okay, so we'll proceed. We'll move on to the second category now. Yeah, okay, we'll move on.
Ma'am, but
So
some
I hope now the trapezium. Yeah, somebody was speaking. Sorry, tell me.
ma'am, some noise was coming, ma'am.
Somebody's audio may be switched on. Just mute your audios. That's why I said you pin my video so that my screen so that you see only what I'm showing. If somebody is speaking, it will get distorted then. Okay. So shall we proceed?
Okay, ma'am.
Yeah. Okay. These are very clear. So moving on to the next variety is the kite. Now, this is something that you have been hearing and seeing around you also. So today what we are going to do is we are going to construct a kite, for which I am going to take you to an applet
Okay.
where I am going to show you how to construct a kite itself.
Okay.
So this is a GeoGebra applet where we are going to construct our kite. So here I am taking the GeoGebra applet to show you how to construct a kite. Deliberately I am doing this because I want to see you, means you have to understand how a kite is formed. There itself you will be able to guess the properties of the kite. So if it is not very clear here, maybe in the next class, I will show it in the app itself. Now you just observe this, all right? Don't get worried too much if there is some confusion or you are not able to see it clearly, etc. I will
Okay, ma'am.
use the applet to show it to you once again in the next class. Okay, now just view this.
All
So
right.
I start with this procedure. I select circle with center through point and I draw a circle. So my circle is ready. Now I again click with the same tool and draw a circle.
Ma'am,
Yes.
we are unable to see what you're doing.
Okay, is it not shared?
No, ma'am.
Just a minute. Sorry. I'll just get back.
Yeah.
Is it visible now?
Yes, ma'am, it is.
Yeah, okay. Sorry, I thought it was visible. Yeah, so I'll start again.
Okay.
So I am going to construct a kite now, for which I have started with drawing a circle through center through point. So first circle is ready. Now my second circle is also ready. Now I have the two circles intersecting at two different points. So let me mark that point of intersect. Because they are intersecting at 2 points, both the points are getting marked here now. So now let me label these points so that I know that these are the points I'm going to concentrate on. A is the center of the first circle. B is the center of the, C is the center of the second circle. Then I have these intersect points which I will take as E and B. Now I'm going to join this AE and AB and further EC and CB and see what I'm going to get. So for this, I will be selecting the line segment and joining AE first, then AB. Now that I have joined AE and AB, do you think they will be equal? Look at AE and AB. And with respect to the circle, just try to imagine what is that component of the circle with center A.
Ma'am, radius.
Yeah, AE is the radius of this big circle. Can you see AE is the radius? Why did you call it the radius?
Ma'am, because it intersects.
Because it is the line segment joining the center of the circle to any point on the circumference. This is how we define a radius. A radius is a line segment which joins the center of the circle with any point on its circumference. So E is a point on the circumference of the circle. A is the center. So when I join A and D, I get the radius of the circle. Similarly, look at AB now. Again, that is also the radius of the same circle. Because here I am joining B with A. B is a point on the circumference and A is the center. So now AB is also the radius of the same circle. Correct? So then can I say AE will be equal to AB? Because they are the radii of the same circle, they will definitely be equal. So similarly, now if I join CE and CB, what are the segments that I will get? I'm going to join C with E and C with P. What are those with respect to the second circle?
Ma'am, radius.
Again, they will be the radii. Why? Because C is the center of the smaller circle and E is a point on the smaller circle. This point E is common between the larger circle and the smaller circle because that is the point of intersect between the two circles. Similarly, B is lying on the big circle and it is lying on the small circle also. So when I join the CE and CB, I am going to get the two radii of the smaller circle. And because they are the radii of the same circle, they will be equal. So that's how I'm going to continue. Just listen. then E, C, and then C, B. Now let me remove all these extra circles which is not required for me now.
Okay.
So once this is removed, I only have this figure here now. So now this figure resembles a figure that you have quite often seen. How does it look like? Maybe if you turn it around vertically, it will resemble a kite. Correct? So when you are making
ma'am.
a kite or when you are constructing a kite, this is how you will do it. So finally, this is representing a kite. Now, with the information I gave you, I said AE and AB are the radii of the same circle, and I know AE is equal to AB. Similarly, CE is equal to CB because those are the two radii of the smaller circle which I used. I removed the circles because I wanted you to concentrate only on this polygon. It is a four-sided polygon, so it's a quadrilateral. So apart from the four sides which enclose this polygon, there is a special feature that you have to see. Here AE and AB are equal, CE and CB are also equal. So AE is adjacent to AB. What do you mean by adjacent sides? When do you say two sides are adjacent for a given polygon?
Ma'am, consecutive sides.
They have a common vertex. When there is a common vertex between two sides, those will become adjacent sides. Alright, so AE and AB, the common vertex is A. So those are two adjacent sides which are equal. Similarly, CE and CB are two sides with a common vertex C. So they are also equal. So a quadrilateral in which there are two pairs of adjacent sides which are equal, then such a quadrilateral will be called a kite. Alright, so this is the speciality of a kite which is coming out of a quadrilateral. Any four-sided polygon, generally we call it a quadrilateral. Now apart from the four sides, there is one special property which this polygon is satisfying. What is that? The two pairs of adjacent sides which are there are going to become equal. If such a condition is satisfied, then I call this quadrilateral as a kite. So we have seen two varieties of quadrilaterals today. I think I'll stop it here because you're getting late for your next class. So from the quadrilaterals, we have moved on to two different varieties, that is the trapezium, and then next we have discussed the kite. So we have tried to understand how these trapeziums and kites are coming out of the quadrilateral. Apart from having four sides, they have some certain properties which are satisfied, and hence they are labeled as a trapezium or a kite. So I think this much, if you understand for today's class, it is enough. I think I will stop it here. We will continue the remaining different varieties of quadrilaterals in our next class. This video which I have shown you now, I shall share the link with you. You can leisurely go through it once again. Maybe you can go through the entire video because I have discussed all the different varieties in the same video. You can see it for today and tomorrow. When I reach back on Thursday for the next class, we can discuss more properties of further different kinds of quadrilaterals. Okay, so we will stop here. I think I'll stop recording first. Then I'll get back. If you have anything that you want to ask me before another 2 minutes maybe, then I will ask you to quit because you have to join your next class.